pendant que la présenter Julienne Stroeve, qui va nous parler dans quelques minutes. Julienne Stroeve est une chercheuse au NSIDC, qui est le National Snow and Ice Data Center. C'est une spécialiste de la télédétection de la glace de mer en particulier, donc elle va nous en parler abondamment. Elle a fait son doctorat en 1996 à l'Université de Boulder à Colorado. Et elle a depuis en fait une activité très importante justement pour étudier cette glace de mer, en particulier avec les satellites. Elle a aussi une activité abondante de communication de la science, aux États-Unis en particulier. Elle est très éclectique, j'ai remarqué dans son CV. Elle a briefé en particulier Al Gore, le prince Albert de Monaco, les ingénieurs de Chevron pour les convaincre du changement climatique qui agit en Arctique, et en particulier aussi des membres de la CIA. Donc, j'espère et je suis sûr qu'elle va nous convaincre maintenant des changements climatiques.
Okay, and I have to apologize. I do not speak French at all, so I will have to give my talk today in English. So what I'm going to focus on today is work that I've been doing in the last few years, where I'm focused just working with the Arctic sea ice and trying to understand what is happening with the sea ice cover and really what it's going to mean for the rest of us if we continue to lose the Arctic sea ice cover. So it's always good to start, since I am just focused on sea ice, to remind us that I'm only talking about the frozen surface of the ocean, so ice that originates within the ocean itself. And here's a nice example of what the sea ice looks, for example, at the end of the summer melt season in September when I was up last summer. And so here's an image of first-year sea ice. It's only about 1 meter thick at this time of year. It's undergone quite a bit of melt, and there's a lot of melt ponds on the sea ice. But sea ice can look very different depending on the time of year. When it first forms, the ocean will have this greasy appearance. It'll look like grease ice. And then eventually those fragile ice crystals will come together, will form pancake ice, which you can see over here, some newly formed pancake ice. And eventually all of those pancake ice sheets will come together, and they will form first-year ice flows. You might get very heavily ridged ice flows. And typically, first-year ice only grows about 1 to 2 meters thick, but depending on how long the ice has been in the Arctic basin, it could be up to 5 meters thick. You can have pressure ridges that are like 10 meters thick. But it's important to distinguish that sea ice does not include land ice. It doesn't include glaciers or ice sheets. It does not include any other floating ice shelves, for example, from ice sheets or icebergs. And I like to make this point because I often see in the media when they're doing a story on sea ice, they'll still show pictures of icebergs, and it's not the same thing. This is not sea ice. And because of that, if the sea ice cover melts, it doesn't directly impact sea level rise. So when we're talking about what's happening to the sea ice cover, it's not going to directly influence sea level at all. That's what the land ice will do. So this figure's already been shown, but it's important to sort of point out that there's a lot of seasonal variability in the amount of the Arctic Ocean that's covered by sea ice at any time of year. And in the wintertime, the entire Arctic basin, Arctic Ocean, is covered with sea ice. But the ice may also extend pretty far south, as far down as the Gulf of St. Lawrence, here in the Labrador Sea, also in the Sea of Okhotsk and the Bering Sea. And it has a spatial extent of about 14 to 16 million square kilometers. And when we're talking about changes in the sea ice cover, there's not a whole lot happening right now to the winter ice cover. There's somewhat of a severely constrained because the Arctic Ocean is surrounded by land. And so there's only so far that the ice cover can expand every winter anyways. And the only real changes that we're seeing right now in the winter ice cover are really in the Kara and the Barents Sea. I mean, that's where we're starting to see some anomalous ice loss that may be impacting weather in Europe. But for the rest of it, there's not a whole lot of changes happening in winter. But in summer, the story's a little bit different. And in summer, you lose all of that seasonal ice. You're losing all the ice in Baffin Bay, Hudson Bay, Bering Sea, and the Sea of Okhotsk. But typically, you've always had some ice in the Arctic Ocean. It might retreat off the coast of Siberia and Alaska, but the central Arctic has historically been covered by sea ice for quite some time. And that, when we're talking about changes happening in the sea ice, we're really focused on what is happening to the summer ice cover because that is what's changing the most right now. And so here, let's hopefully this works, is a movie that shows what's been happening to the summer sea ice cover, basically looking at the changes in the spatial extent of the sea ice cover at the end of September, the end of the melt season. over time from satellite data. And right now we have about 35 years of really good observations from satellite with which we can characterize what's been happening to the sea ice cover. And so you can see that there's quite a bit of interannual variability in the ice cover, and some years you might have less off the coast of Alaska, some years you might have less off the coast of Siberia. But in the last few summers, what's been happening is that it's not just less ice over Alaska or Siberian sector, it's less ice throughout the Arctic Ocean. And this is very different because if you look at these peaks and dips in the sea ice cover back in the 1990s, those tended to be dominated by, you might have 1 year with less ice off the coast of Alaska, 1 year with less ice off the coast of Siberia. But these last few summers, where you've had very large drops in the sea ice cover, its reductions Arctic-wide. And so if we look at this, and we just look at the last several years where we've had very anomalously low sea ice cover at the end of summer, you find that a large, vast amount now of the Arctic Ocean is ice-free. And you can look at things like the Northern Sea Route or the Northwest Passage. These have been open since 2007, every summer. And if we look at just the long-term trend in the sea ice cover, we find that it's declining right now at a rate of about 14% per decade, which represents about a 40 to 50% reduction in the amount of the Arctic Ocean that was covered by sea ice, 40 years ago than it is today. And it was interesting, in 2007 we had quite a large drop. We had 1.6 million square kilometers difference in sea ice extent from 2006 to 2007. And that took a lot of scientists by surprise. We didn't think that the ice could drop that much in a single year. But then in 2012 it happened again. And 2007 was interesting because we had sort of what we would call a perfect storm setup. We had very favorable weather conditions that summer for ice loss. And so a lot of ice was melted in 2007. 2012, though, we didn't have sort of that perfect storm set up that could have taken away a lot of sea ice, and yet we had a new record low, which is now at 3.41 million square kilometers for last year. So, of course, what we want to understand is, why is this happening? What is causing the sea ice cover to retreat? And there's a lot of different feedback processes that are operating together that are helping to take away a lot of ice every summer. And one of the first things that we've noticed is it's just warmer in all seasons. The last decade has seen anomalously warm temperatures regardless of what month it is, whether it's winter or summer. It's just warmer in the Arctic than it used to be. And one of the things that's going to happen if you have warmer temperatures is you're going to have thinner ice in the springtime. The ice is not going to grow as thick during the winter. It's going to be thinner. And of course, if you have thinner ice, it's also going to have more open water at the end of the summer melt season because thinner ice melts out easier than thicker ice. The other thing that happens, if you have a lot thinner spring ice, open water areas, once the melt season kicks in, are going to develop earlier in the melt season than they used to. And we're seeing trends towards earlier melt onset. You have earlier formation of open water. And if you have that, you're going to enhance this ice albedo feedback because the ice tends to reflect most of the incoming solar radiation back out to space. If you have now more earlier development of open water, you can absorb more of that sun's energy by the ocean and it helps melt more ice. And this feedback process is always operating in the Arctic during the summertime, but because you have thinner ice and because melt is happening earlier, you're just enhancing that ice albedo feedback. And the other consequence, of course, of more open water in September is then the ocean's been absorbing a lot more of the sun's radiation during the summer. And before the ice can freeze again in winter, it's going to have to release all of that heat it gained back to the atmosphere before the ocean can freeze again. So you're seeing this big pronounced warmer autumn temperatures that then is going to impact on thinner spring ice again. So you have a lot of competing feedback processes that are operating to help keep the ice in the state that it's in right now. So an example of sort of these feedback processes, so first we can look at what are the changes in air temperature happening in the Arctic. And this is air temperature that's averaged from 60 to 90 degrees north. And we're looking at it as a function of year here on the x-axis and month on the y-axis. And you can see these are temperature anomalies. And if we look, earlier in the last couple decades, you might have periods of colder than usual temperatures or warmer than usual temperatures. But this last decade, it's just been warmer in all seasons. And so this is one of the things that, of course, is influencing the ice growth and the ice thickness is that it's just a lot warmer than it used to be. And because of that, we're seeing earlier formation of open water in the Arctic. The melt season is happening earlier than it used to, sometimes in some regions up to a month earlier than normal. And so we can look at trends, for example, in the sea ice concentration. And we're looking at May, June, and July. And you can see that earlier in the melt season, you're getting earlier formation of open water in the Chaire and the Barents Sea, for example. But by June, that starts to spread also to the Beaufort Sea and the Chukchi Sea. And then by July, you're seeing much larger negative trends in the sea ice concentration. And so what that means, of course, if you are now forming open water areas earlier, you're going to enhance that ice albedo feedback mechanism that's already in operation in the Arctic. And so, I mean, we can look at this schematically. If you look, even like back in the 70s when most of the Arctic Ocean was covered by sea ice, a lot of that sun's energy is being reflected back out to space. It's not helping to warm the Arctic at all. But if we look at today and we see this big pronounced retreat of the sea ice, all of a sudden now the ocean is absorbing much of this heat because it has a much lower albedo than the ice cover. And so therefore, the ocean's warming up, and that's going to be melting a lot more ice than it used to. And we can see this if we just look at the accumulation of the total absorbed solar radiation that's happening for each month in the summer season, and just see, where are the regions where we're having a lot more absorption of solar radiation. And as you would expect, it's going to match where you've been losing the sea ice. So we can look in the early part of the melt season in May, and you have much positive anomalies, for example, in the Chaire and the Barents Seas. And these just start to spread and become more Arctic-wide as the summer progresses. And so we're seeing just a lot more absorption of solar radiation by the ocean and ice system. And if we look in August, I mean, locally, some of these anomalies exceed 150 megajoules per meter squared. And this could melt an extra about 50 centimeters of ice. So obviously, if you're forming these open water areas earlier, you're just enhancing how much more ice you can melt during the summer melt season, because the melt season is getting longer, and you can melt a lot more of the ice. At the same time that we have been losing the spatial extent of the sea ice cover, the ice is also becoming a lot thinner. I mean, typically the ice forms every winter when it gets cold enough, the sun goes down, the temperatures get cold, the ice forms. And a lot of this ice does stick around for many years. And if we look at, for example, ice age, and so we're doing this by tracking each individual ice parcel, and if it survives the summer melt season, we age it another year. So in this figure here, red is ice that's at least 5 years or older. The dark blue is just first-year ice, so ice that just forms through one winter season. And then you can see different shades, so this is second-year ice, and the green is third-year ice, and the yellow is fourth-year ice. And you can see in the 1980s, most of the Arctic basin consisted of old ice. And as we go through time, and we look now at 1995, we see we're starting to get a reduction in the amount of the really old ice, so the ice that's at least 5 years old. And part of this happened because we had this positive phase of the Arctic oscillation during winter for several years in the late 1980s, early 90s, that helped to transport a lot of this old ice out of the Arctic basin through Fram Strait. So some of this ice loss was just a result of changes in transport. But then we go to 2005, for example, and we start seeing, well, we have quite a bit less old ice again. More of the Arctic basin is becoming first-year ice, less of it's multi-year ice. And then by 2013, if we look at where we are right now, we have less than 5% of the Arctic Ocean is now covered by ice that's at least 5 years or older, and the majority of it, 73% of it, is actually now first-year ice. And this is significant because if you have an Arctic basin dominated by first-year ice, again, the ice grows about 1.5 to 2 meters thick every winter. This ice can melt out a lot more easier in the summertime than this thicker, older ice. And so this change that's happening in just the age of the ice, how much of that old ice that is there, and what is the fraction that's really old versus maybe 2 or 3 years old, that has changed. And because of that, you can't really keep the ice around in the summer melt because it's just a lot thinner than it used to be. And we can look at this. We've looked at this a little bit by comparing ice age data with thickness retrievals, for example, from NASA's instrument, the ICESat laser altimeter. And we're just looking here at age on the x-axis and thickness from ICESat from 4 different years. And we find that there tends to be a linear relationship between how old the ice is and how thick the ice is, which would make sense. So the longer that the ice has to spend in the Arctic basin, the thicker it grows. And so if you look at these changes in ice age, it's really reflecting a change in the overall thickness of the Arctic basin, of the ice that is there. But interestingly enough, this was through 2007. If we look now at the last 2 years and we incorporate data from 2008 and 2009, we find that that relationship is starting to change. And so where we used to see some of this older, thicker ice would be at least 3 meters, 3.5 meters thick, these older ice classes, so ice that's older than 5 years, is only about 2 meters, 2.5 meters thick now. So it's thinner than it used to be, and it's actually getting to the point where it's as thick as some of this younger multi-year ice, so maybe as thick as like the third-year ice and second-year ice. So the relationship seems to have changed in recent years. And we can see that this is really where the albedo effect really comes into play, because if we look at, for example, how much melting happened following the summer of 2007, where you had a significant amount of open water in the Arctic basin compared to the last few years before that, this ocean absorbed a lot of the summer heat. And if you look at buoys in the Arctic basin, you look at it here by the North Pole and you look at it in the Beaufort Sea, you find that there was a lot of bottom melt that happened in 2007. So this blue line here is in the Beaufort Sea, and this shows the amount of bottom melt that happened, which was about 2 meters. And so those older, thicker, multi-year ice flows, it looks like they got thinned quite a bit by the amount of heat that was absorbed by the summer. So that could be one of the reasons why now that old ice in the Arctic basin is not as thick as it used to be. And that's why it's not surviving any more of a summer melt season. If we look at the surface melt between different years, and so we're looking, I have 1975 through 2007, there's not a whole lot of variability in the surface melt. That doesn't seem to be playing as large of a role as this bottom melt. So if you have earlier formation of open water and that ocean is absorbing that heat in summer that should be reflected back out by the ice, you're going to melt a lot more of it in the summer season. And of course, there's other factors, though, too, behind the ice loss. And one of the things is that I mentioned just a little bit ago, the positive phase of the winter Arctic oscillation in the late 80s and the early 1990s. And if we just look at the time series of the winter Arctic oscillation index, we find that, it was mostly in a negative phase, but you had this period of a very strong positive phase in the late 80s and the early 90s. And this, in effect, strengthens the transpolar drift stream, helps to flush a lot more of the older ice out of the Arctic basin. But since that time period, it's oscillated between positive and negative phases. And interestingly enough, in winter 2009, 2010, the Arctic oscillation was in its most negative phase that we had seen. And yet, and what that typically would do is it would help strengthen the Beaufort Gyre, so it would help increase the circulation of the old ice that's north of Greenland and the Canadian archipelago into the Beaufort and Chukchi seas before it comes back into the central Arctic. It's a process that we usually associated with having more summer sea ice. But actually, in that year, we lost a lot more summer sea ice. So the old ice that came up into the Beaufort and the Chukchi Sea actually melted out instead of coming back into the central Arctic. The other thing that we've noticed in the last several summers is there's been a dominance of what we call the Arctic summer dipole anomaly. So looking at, this is sea level pressure and anomalies. And just so this is Greenland right here, and here's Alaska and Siberia. And so under the dipole anomaly, you have stronger positive sea level pressure anomalies over the Beaufort Sea and the central Arctic, combined with very negative, lower than normal sea level pressure anomalies over Siberia. And one of the things that this does is, one, it evects a lot of warm air from the south into the Arctic region. So this is in 2007, we had a very strong dipole anomaly, and you brought in a lot of warm temperature. So this is temperature anomalies for June, July. And you can see this big heating here where you lost a lot of sea ice in 2007. The other thing that it does is, because of this really strong pressure gradient, you generate very strong winds that help push the ice away from the shore of Siberia and Alaska towards the pole. So this is one of the factors that contributed for sure to the 2007 minimum. This pressure pattern has been setting up almost every summer since 2007 and being pretty consistent in the summer months, except last summer, which is really interesting because last summer was dominated by storms. And it's a pressure pattern that historically, if you look statistically over time, should have actually caused the ice cover to spread out more and have more sea ice. But in fact, that didn't happen. It still melted out, and we had a new record minimum. So even when we look at some of these circulation changes, it seems like the rules are changing. So circulation patterns that used to help keep the ice aren't doing it. The ones that help take away the ice are even more effective at doing so. And finally, another factor that is a little bit more poorly understood, but there has been documentation of intrusion of warm waters coming into the Arctic through the Bering Sea and also through Fram Strait. And so we know that this has been happening, but one of the things is that we're not sure how much mixing of those warm water flows is happening with the sea ice. And this is an area of active research. This is a paper recently published by Woodgate, which is showing, just looking at changes in the Bering Sea inflow and heat flux. And because the Bering Sea is actually rather shallow, it's likely that some of this inflow of warm water from the Bering is helping to melt the sea ice. But again, there's a little bit of uncertainty as to how much mixing is happening. But we do know that any small change in ocean heat flux into the Arctic is going to have a very large change on the ice thickness. And I think this is one area of research that needs to be, more emphasis has got to be put on that to better understand the role of the ocean forcing in causing the ice loss that we've been observing the last several years. Another culprit that people have talked about is just black carbon on snow. I mean, obviously, if you have more deposits of black carbon onto the snow, you're going to lower the albedo, you're going to enhance the melt. But there's not that much known as to how much black carbon is being deposited on the sea ice and on the snow cover, and how much that is enhancing the melt. But obviously, this is probably likely also a factor as well. So, I mean, it's one of the things that I get a lot when we talk to the media, of course, is everybody wants to understand, well, why does this matter? So why do we care if the Arctic loses its summer ice cover? And one of the things that we're already seeing, and this was shown a little bit in the other talk, is that when you lose the ice cover, you warm up the Arctic. So if you have an ocean covered by sea ice, I mean, you have transfers of heat with sensible and latent heat, but it's not that large compared to if you lose the sea ice, all of a sudden you have large transfers of sensible and latent heat flux between the ocean and the atmosphere, because the ocean cannot freeze again until it releases all the heat it gained in the summer. And this is going to cause the atmosphere to warm. And we see this warming not just at the surface where you've been losing the sea ice, but it's also extending through depth in the troposphere. And if we look at that, so we can just look at the warming, for example, over time, and we can look at the Arctic, which is a light blue line, and we can compare it to the mid-latitudes and the tropics in the southern hemisphere. And you can just see all of a sudden the Arctic has been warming quite a bit in the last few years. And this warming is definitely somewhat seasonal. It's most pronounced in the autumn, but it also is happening in the springtime as well. But obviously, the temperature gradient between the poles and the equator helps drive a lot of our atmospheric and oceanic circulation. And so if you change that temperature gradient, it's going to impact on circulation patterns. And we can see, too, that this warming effect that we've been having in the Arctic is also starting to show itself in terms of the poleward thickness gradient. And we can see that over the last several decades, the poleward thickness gradient has decreased. And this is trends right here in the poleward thickness gradient as a function of longitude. The red ones are the ones that are statistically significant. And so you can see that there's been this trend and a decrease in that thickness gradient between 40 and 30 degrees north compared to 80 to 70 degrees north during the fall. And this is what you would expect, of course, because that's when you're having the largest anomalous heating from the loss of a summer sea ice. And why this is important, of course, is the changes in all these meridional temperature and thickness gradients is going to influence the structure of the atmospheric zonal flow. It's going to influence the jet stream, which is then going to impact on weather in the lower latitudes. And this is some of the work that a colleague of mine, Jennifer Francis, has been doing, and she published a study in 2012, where she's looking at changes. This is a thickness difference seasonally as a function of year. And we can see that basically the winter and the fall is where you're having negative changes in the poleward thickness gradient. And she looks at how that then impacts zonal wind speed. And she can see that the zonal wind speed has also been declining during the same time that you're having this change in the poleward thickness gradient. And this change in the zonal flow is going to alter both the vertical Rossby wave propagation as well as the meridional propagating waves. And the weakening of this extratropical zonal flow appears to be connected to increases in the incidence of blocking events in the North Atlantic that could cause cold air outbreaks during winter. So if we look at the Snowmageddon in the East Coast in 2009 and 2010, that was connected in part to having these blocking events during winter that actually happened at the same time where we had a strong El Nino that brought a lot of Pacific warm flow up into the Arctic, up into the East Coast as well. But I would say, though, that some of these links right now are a little bit uncertain because we have only had a few years of very, very low sea ice concentrations. And so if we're looking at a statistical robustness of these links between changes in the atmospheric circulation and changes in the sea ice, we really don't have enough data, I think, to really firm up a lot of these hypotheses right now that we're looking at as to how the sea ice could influence the weather here in lower latitudes. But one of the things we also do see from modeling experiments is that when you run these model experiments and you force them with reduced sea ice cover, a lot of them are showing a dominance of the negative phase of the Arctic oscillation, which means higher than normal sea level pressure over the Arctic. So you get higher pressures, you also tend to have warmer air temperatures over the Arctic, and that tends to create more blocking events here in the North Atlantic, which has potentials for more severe winters in the eastern U.S., as well as in the UK and East Asia as well. Now, this is based on modeling experiments, and if we look at just the observational record, I mean, the last couple of winters have been dominated by the negative Arctic oscillation, but that's not always been the case. So obviously there's more things going on in the atmosphere, but this is one of the sort of dominant signals that are coming out of climate model studies that we would expect to happen as the sea ice cover continues to retreat. Of course, if you look just within the Arctic itself, obviously the loss of sea ice combined with warmer temperatures and permafrost thawing is having large impacts on coastal communities. And there's several coastal communities that are being forced to move because they're falling into the ocean. And so one of the studies that I'm starting that I haven't quite done a whole lot on yet is to just look at the impact of losing the sea ice cover, exposing these coasts to more waves, but also looking at how having more open water is going to influence storm development in the Arctic. I see a clear link between loss of ice and increased storminess in the North Atlantic, but not necessarily here in coastal Alaska, where we're seeing some of the largest coastal erosion amounts happening. So it's a bit unclear, but obviously this is an area of active research as well. And of course, the permafrost carbon cycle is quite important. So as you lose the sea ice cover and you're warming the Arctic atmosphere, climate model simulations show that this warming can spread up to 1,000 kilometers inland. And we're seeing already that permafrost is thawing in the Arctic. Temperatures are warming. And this is important because if you look at the current estimates of the amount of carbon that is stored in the permafrost, right now they're thinking it's about 1,600 gigatons of carbon, compared to about 730 gigatons of carbon in the atmosphere today. So there's a huge feedback process that's looming as we continue to warm up the Arctic more and as we lose the snow and ice cover in the Arctic. There's also been an impact, of course, on the Arctic tundra. There's many studies that have been reported in the recent years talking about the greening of the Arctic. So how losing the sea ice cover locally warms the coastal regions. So we can look at the sea ice concentrations and the warming index that's because of the losing of the sea ice, and how that is both lengthening the growth season in the Arctic for plants, and just looking at the changes in the plant growth. And you see positive changes all over the tundra regions in the Arctic, directly as a result, apparently, from losing the sea ice and warming the Arctic, and increasing the amount of sensible and latent heat flux. Other implications of summer sea ice loss. One of the few studies have been looking at changes in cloud cover in the Arctic, and I think this is an important area of research which is not all that well developed at the moment, but certainly looking at the cloud radiant feedbacks. If you have more clouds developing in the Arctic, and we see this in spring and we see this in autumn, how that impacts on the energy balance in the Arctic and how that impacts with the amount of downwelling radiation and influencing on ice growth, for example, or prolonging the melt season. We have been looking at changes in water vapor, which would make sense if you're losing the sea ice cover and you have more transfer of sensible and latent heat flux to the atmosphere. You can get trends in the amount of precipitable water and humidity in the Arctic. And we are seeing these positive trends in the winter, or I should say autumn, but we're also seeing them in summer as well. This in the North Atlantic, I'm not entirely sure what's causing that. It seems to be partly related to increases in sea surface temperature in this region and not directly related to the ice. But we see this in many different data sets when we look at changes in precipitable water and humidity. And of course, there's a lot of implications in terms of commercial shipping and just politics in general in the Arctic. I know in this last year, there was 48 vessels that traveled through the Northern Sea route that carried more than 1.2 million tons of cargo, compared to 34 in 2011 and 4 ships in 2010. So the shipping impact right now in the Arctic, and this is becoming a very viable route. The Northwest Passage is probably going to take a bit longer, I think, to become a more viable route, although it has been ice-free the last several summers as well. But there's a lot of pressure right now in the Arctic in terms of shipping. And it's not just shipping from doing cargo. I mean, there's tons of shipping activity in the Arctic, whether it's fisheries, whether it's tourism that's been increasing, especially around Greenland. There's been a lot of tourist ships that have increased. So there's a lot of pressure in the Arctic right now with resource development, which we can look at here too if we just look at the estimation of how much natural gas and how much oil there is in the Arctic. They estimated in 2008 that there's about 90 billion barrels of oil and 1,700 cubic feet of natural gas within the Arctic. And most of this is located offshore. And so there's a lot of undiscovered natural gas over on the Eurasian sector, also over in Alaska, and this is the undiscovered oil fields. And there's a lot of effort, of course, to start tapping a lot of these fields, especially now that the sea ice is retreating as much as it has been. And of course, we have to also think about it's not just other impacts like weather or human communities, but it's also the entire ecosystem of the Arctic. And you think about, of course, there's ice-dependent species such as polar bears or walrus and seals that are going to be impacted by the changes of the sea ice cover, but it's not just those species. I mean, the timing of when the ice forms and retreats also impacts the phytoplankton, which feed the fish, which feed the seals, which feed the people. And even just looking at disease distributions and how diseases are going to change and how certain regions that were isolated because of the sea ice are now becoming more accessible by other species, how that's going to impact on the whole ecosystem of the Arctic is an area of very active research right now as well. So just briefly talking about the future, I mean, if we look at future climate projections and we look at what's going to happen for the planet as a whole, and we look at warming of about 2 to 3 degrees Celsius, when we look at the Arctic, a lot of these warming projections are at least 2 to 3 times that. And that, again, is because of that ice albedo feedback, because if you take away the snow and ice, you're just going to warm the region by a lot more than the rest of the planet. So we're looking at temperature increases that could be as high as 7 degrees Celsius by the end of the century. And what that means is that if we look at our climate model simulations, all of them say we're going to lose the summer sea ice cover at some point in the future. And this is an update of a study I did in 2007, then we published again in 2012. We're just looking at comparing the observed record of sea ice cover for September, and this is a black line, and compare that to the blue is the models that were used in the 2007 IPCC report, and the red are the models that will be used in this year's IPCC report. And one of the things that this graph shows is, one, qualitatively all the observations are in agreement that the ice cover has been declining over the last 50 years. They're able to somewhat simulate the hindcast, so the ice conditions like in the 1950s and 60s and 70s are kind of getting that right. But when we look at this last decade, even though the CMIP5 models they'll be using the next IPCC report are doing a better job overall, they're still very conservative in regards to the ice loss. Most models do not have trends as large as that are observed. And so when we look at these projections as to when we might transition to an ice-free Arctic, I mean, in the CMIP5 models, about 50% of the models say we should be ice-free around 2060. But we're looking here at the observations. I mean, it's still a lot faster than what's happening. So there's different feedback processes that are probably still not very well captured by a lot of these models. The other thing that I find interesting is that the spread between the model projections has not really changed. So when we're looking at uncertainty as to the timing as when this might happen, that hasn't really changed between the modeling efforts, which I think is a bit disappointing that we can't actually improve the uncertainty as to when this may happen. And then finally, I just wanted to talk about accelerated permafrost thawing, because I think this is going to be a big feedback that we need to look at. But if you just look at the reductions in the amount of area of the Arctic covered by permafrost, we can see the dark purple here is what it is from the last sort of 50 years, and then this is where it's forecasted to be in the next towards the end of the century. And by losing all of this permafrost, this frozen ground, there's that huge carbon feedback from when all these active layers starts to thaw and all those critters get active and start releasing methane. So just to conclude, it's obviously that we're quickly losing the sea ice cover. It has accelerated in the last decade, and it seems like it doesn't matter so much what's going on with the weather patterns. We're still losing the ice cover, and we're starting to already feel the impacts of this. The most prominent impact that we're already noticing is Arctic amplification. But if we look at when we might expect ice-free summers, we still sometimes say around 2030, just because the observations are showing it happening so much faster than the models are capturing. But we do know that Arctic amplification is going to be a big issue because it impacts weather patterns, it impacts permafrost, and I would say, though, I'm a little cautious still on this just because the robustness of these linkages are still quite unclear. This is an area of very active research, and there's a lot more that we need to understand about how this is going to impact weather, especially here in lower latitudes. But there's going to be a lot of impacts on terrestrial warming and the carbon cycle, and also the geopolitics of Arctic. I mean, there's a lot of changes happening that a lot of countries are now interested in and trying to figure out how best to maneuver these changes and to correctly use the resources and use them wisely. Okay, thank you.